Hello students, welcome to the unit 8 of this course Electromagnetic Theory 2 and Theory of Relativity. This is part B, Theory of Relativity. The name of the unit is Relativistic Kinematics and the module name is Derivation of the Lorentz transformations and Derivation of its consequences such as length contraction and time dilation part 1. I am Yatin Desai, Assistant Professor in Physics, Chowgali College, Margao. The outline of this module is derivation of Lorentz transformation equations. Learning outcomes. At the end of this module, you will be able to derive Lorentz transformation equations and you will be able to reduce Lorentz transformation equations to Gaussian transformation equations for V much less than C. Derivation of Lorentz transformation equations. Here we consider two frames S and S dash. Frame S is fixed in space and frame S dash is moving with uniform velocity v along the x-axis with respect to the S frame. At time t equal to 0, origins O and O dash coincide and the axis x, y, z coincide with the axis x dash, y dash, z dash. That means these axes lie onto each other. Consider an event in one initial frame S characterized by its location and time specified by the coordinates x, y, z, t. In the second inertial frame, the same event is recorded by the coordinates, space-time coordinates x dash, y dash, z dash, t dash. Now, we seek the functional relationship between x dash, y dash, z dash with x, y, z, t. And we seek the relationship of the type x dash, which is a function of x, y, z, t, y dash, which is a function of y, x, y, z, t, and z dash, which is a function of x, y, z, t, and t dash, which is a function of x, y, z, t. That is, we want the equations of transformations which relate one observer space-time coordinates, that is x dash, y dash, z dash, t dash of an event with the other observer's coordinates of the same event, that is with x, y, z, and t. We shall use the fundamental postulates of special theory of relativity and the assumption that the space and time are homogeneous, that is, all points in space and time are equivalent. Let S dash frame move with the relative velocity v along a common x dash axis and by keeping the corresponding planes parallel. When origins O and O dash coincide, let both the clocks read time t equal to 0 and t dash equal to 0 respectively. Homogeneity assumptions require that transformation equations must be linear. That is, they involve only the first power in the variables. So, the general form of transformation equations are given as follows. X dash is related to x, y, z and t after multiplying with them with the constants a11, a12, a13, a14 and then adding them together. Similarly, y dash is a21x plus a22y plus a23z plus a24t. Z dash is given as a31x plus a32y plus a33z plus a34t. T dash is given as a41x plus a42y plus a43z plus a44t. Now, if you notice here that there is a linear relationship, that is the order or powers of this x, y, z and t everywhere is 1. If you try to do this for the higher powers of x, y, z and t, then there will be some problem. And to understand what happens exactly if you do not follow the linear relationship, okay, what happens is to be investigated in the problem that I have given you in the model assessment. Now, in these above equations, subscripted coefficients such as a11, a12 and so on are constants which must be determined to obtain the exact transformation equations. Unless and until we determine these 16 coefficients, okay, we cannot get the exact transformation equations. Now, if v is 0, it depends upon the value of the velocity. The values of 16 coefficients depend upon the value of velocity of two inertial frames. If v is 0, then we have seen that x, y, z was coinciding with x dash, y dash, z dash. In that case, a11 would be 1, a22 would be 1, a33 would be 1 and a44 also would be 1 and rest all the coefficients would go to 0. Similarly, when the second frame is moving with a velocity v, then we get the Galilean transformation. Galilean transformation, we know that x dash is x minus vt. In that case, a11 is 1, a14 is minus vt, a12 must be 0, a13 must be 0. Then y dash is y, that means a22 is 1 as we have said before. Rest other constants will go to 0. Z dash is z, t dash is t, so a41, a42, a43, a44 is 0. This is at the lower speed. But when v is comparable to the speed of light, we say that Galilean transformations are not useful and we have to go for the Lorentz transformation equation. This is what we are doing now. So we seek to find equations for any value of v that is as a function of v. To determine these values of 16 coefficients, we use postulates of relativity, namely the principle of relativity. That is, no preferred inertial system exists, or the laws of physics are same in all inertial systems. The second one, the principle of constancy of speed of light. If the speed of light is in free space has the same value c in all inertial systems. Next, let us consider that x-axis coincides continuously with the x-dash axis. As we have drawn our reference frame as this. This is S frame, this is S-dash frame, this is x-axis and this is x-dash axis. So they are along the same direction. If they coincide, then we will have at the x-axis the value of y is 0 and z is 0 in S frame, and y dash is 0 and z dash is 0 in S-dash frame. So if you look at the transformation equations, only y dash and z dash. For y dash to be equal to 0, we need y to be equal to 0 and z to be equal to 0. So y dash is 0 when y is 0, z is 0, but we cannot say anything about these two terms a21x and a24t. So for that equation to be satisfied, we must take a21 to be equal to 0 and a24 equal to 0. So we have fixed our two constants a21 and a24 to be equal to 0. Similarly, z dash is 0 when z is 0 when x and x dash axis coincide. If z dash is 0, z dash will be 0 when y is 0 and z is 0. So we cannot say anything about this x term and then t term. So the multipliers to these two terms a31 and a34 must be fixed to 0. So we are fixing another two coefficients, and in that way we get the yz formulas as y dash equal to a22y plus a23z and z dash equal to a32y plus a33z. And we have seen that the constants a21, a24, a31 and a34 are all 0. Similarly, here we have the xy plane. Now I can draw that diagram once again. This is S frame, this is the origin O, axis x, y and z, and similarly this is the S dash frame, axis O prime, x prime, y prime and z prime. This is moving with the velocity v. Now if you consider the xy plane, which is this plane, and x dash y dash plane, which is this plane, this xy plane is characterized by z equal to 0 in S frame, and x dash y dash plane is characterized by z dash equal to 0 in the S dash frame. Similarly, xz plane, this plane is characterized by y equal to 0, and this x dash z dash plane is characterized by y dash equal to 0. Fine. So if you consider the yz plane and y dash z dash xy plane and x dash y dash plane, then y is 0 and y dash is 0. So when y is 0, y dash will be 0, but this term is creating a problem. Okay, so to fulfill that condition that y dash is 0 when y is 0, we must take that a23 equal to 0. So we are fixing one more constant a23 to be equal to 0. And same is the case for the xz plane. Xz plane is characterized by y equal to 0 here, and x dash z dash plane is characterized by y dash equal to 0 here. So in order to fulfill z dash is 0 when z is 0, but this term must be 0. It should not exist to fulfill that condition. So we are fixing one more constant a32 to be also equal to 0. So we are ending up getting the simple equations for y dash and z dash as y dash equal to a22y and z dash equal to a32y, which are shown here. So there are two remaining constant coefficients here, which is a22 and a23. To evaluate these constants, we use the relativity postulate. We first illustrate for a22 and then we will say that similarly it can be evaluated for a33 as well. Now to evaluate a22, suppose that a rod of unit length is lying along the y-axis of the S frame. So this is our S frame. This is origin O, S frame. This is axis X, axis Y and axis Z. And we say that a rod of unit length is lying along the y-axis. So one end of the rod is here at y equal to 0 and another end of the rod is here at y equal to 1. So according to S dash observer, which is this frame moving with velocity v dash, okay, S dash, this is x dash, y dash and z dash. According to this observer, what is the length of this unit length rod here in S frame? That is given by the transmission equation, that is y dash equal to a22y, and since y is 1 here, y dash equal to a22 times 1. So according to S observer, the length is a22 times 1. This is as per the S dash observer, the length measured by the S dash observer. Now suppose that the same rod is brought to rest and along the y dash axis in the S dash frame. So now this is the S dash frame, this is the y dash axis, x dash axis and z dash axis. This is moving with velocity v. And now we are bringing the rod here at y dash equal to 0 and y dash equal to 1. So as according to S dash observer, the length of the rod is 1. But what is the length of that same rod measured by S observer? So this is given by the transmission equation. We have that y dash equal to a22y. So y is equal to 1 by a22 times y dash and y dash is 1. So y measures that distance as 1 by a22 times 1. Okay, so there is a problem here that when the rod is kept in the S frame, its length was measured by that moving observer as a22 by 1. And if the rod is placed in the S dash frame, its length is measured by the S observer as 1 by a22 times 1. The measurement of the rod should be same as per the postulate of relativity. The laws of physics are invariant under the inertial frame of reference. So 1 by a22 times 1 should be same as equal to a22. So that's why we write that a22 be equal to 1 divided by a22, and because of which we get that a22 is equal to 1. Therefore, we fix one more constant as a22 be equal to 1, and similarly with the same reasoning we can determine and say that a33 is also equal to 1. Therefore, our transformation equation become y dash equal to y because a22 is 1 and z dash equal to z because a33 equal to 1. Now there remains the transformation equations x dash and t dash, which are given as x dash equal to a11x plus a12y plus a13z and a14t, and t dash is a41x plus a42y plus a43z and a44t. So now these 8 constants are remaining to be determined. Let us look at the t dash equation, which is this. For reasons of symmetry, we say that t dash does not depend upon y and z because the direction of motion is along x axis. Otherwise, clocks place symmetry along in the yz plane, such as at plus y and minus y or at plus z and minus z, along about the x-axis would appear to disagree as observed from S dash, which would contradict the isotropy of shape. That means if I place a clock here at plus y and minus y, x z coefficients are same. So it is x comma plus y comma z and x comma minus y comma z. If we place these two clocks, they should measure the same time. So it is independent of y. Similarly, if I place a clock here, x plus y plus x comma y comma z and x comma y comma minus z, these two clocks also should measure the same time for the same event. Otherwise, that isotropy principle will be violated. Hence, in the time equation, that y, it is independent of y and z, so we are fixing a4 to be equal to 0 and a43 to be equal to 0. Similarly, for the x dash equation, which is given by this, we know that at a point having x dash equal to 0 appears to move in the direction of the positive x-axis with the speed v. So that x dash is 0 and must be identical to the statement x equal to vt. We can show it like this. This is S frame and this is x dash frame. This is x dash, this is x, and this is moving with the velocity v. So at some time t, okay, when the origins O and O dash, which were coinciding at t equal to 0 and t dash equal to 0, but after some time t, S dash has moved to distance equal to vt, and at that time x dash is same 0, but x is equal to vt. So we expect that x dash is a11 times x minus vt to be the correct transformation equation, because if you substitute x equal to vt, you will get that x dash equal to 0, because when x is equal to vt, x dash is equal to 0. So in our transformation equation, which is here, we write this x dash as, because they are independent of y and z, we also fix this to be equal to 0, this to be equal to 0, and write it as only a11x and a14t. So since we had x dash equal to a11 x minus vt, okay, that is also equated to our original transformation equation. We can write a11x equal to a11 vt equal to a11x plus a14t. So from here we see that a14 is minus va11. So we have fixed one more constant, but in terms of another constant a11. So if you substitute back in our original transformation equation, we had a11x minus plus a14t, now a14 is minus v, so we get a11x minus vt. And we already have y dash equal to y, z dash equal to z, and t dash is a41x plus a44t. So now these equations are still incomplete because we have not yet determined the constants like a11, a41 and a44. And to determine those constants, we use the second principle of relativity, that is the principle of constancy of velocity of light. Let us assume that at time t equal to 0, a spherical electromagnetic waves leave the origin S, which also coincides with the origin S dash at that moment. That means we had two frames of reference, okay, S and here, and S dash also, which were actually coinciding at time t equal to 0. Okay, and we have created an event here like a flashing a bulb. So a spherical wave front from this point will expand. Okay, so and after that event occurred, S dash moves in the forward direction with a velocity v. Okay, and for him also, because the time speed of light is same for him, it is not different. So he will also say that there is a spherical expansion of that wavefront, spherical wavefront. Okay, from his origin at the center of that wavefront. Now we know that the wave propagates with a speed c in all directions in each inertial frame. Its progress is then described by the equation of a sphere whose radius expands with time at a rate c in terms of either the primed or unprimed set of coordinates. That is, in the S frame, the equation of sphere is written as x square plus y square plus z square is c square t square, equation number 4. And in the S prime frame, we have it as x prime square plus y prime square plus z prime square equal to c square t prime square. This is equation number 5. Now, according to the principle of constants of light, both should agree with each other. That's why we substitute in place of x dash, y dash and z dash as well as t dash the equations which are given by equation number 3 altogether. So if you do that, we get it as x dash x square, right? It is x dash square, which is a11 x minus vt. So we should write it as a11 square x minus vt whole square plus y dash square is y square plus z dash square is z square plus t dash square, which is c square a41 x plus a44t whole square. Now rearrange these terms. Now you can expand this square term, you can expand this square terms. Now there is a x square term, there would be x square term here, there would be x square term here. This you can shift it from the right hand side to the left hand side, this term, it will be a negative term, and if you collect all x square terms together, it will be a11 square minus c square a41 square x square, then y square is written here, z square is written here, then the middle term is the xt term, so you can collect it from this term as well as from this right hand side, bring it on the other side, it will become with a minus sign, you can take the minus 2 common there, so it is v a11 square plus c square a41 a44 xt is taken out, and other side t square, which is a term here, you can take it on the other side and combine with this t square term. So that will be c square a44 whole square minus this v square a11 square, and t square is taken out. This is negative because we are taking this term onto the other side. Now this equation is similar, should be similar to x square plus y square plus z square equal to t square. That is equation number 4. Now for that equation number 4 to agree with this, we must fix that this must be equal to 1. That's why we are writing a11 minus c square a41 square equal to 1. This middle term is not actually, the xt term is not there in that equation number 4. So this should be written as 0. So we have written it as v a11 square plus c square a41 a44 equal to 0. And if you see, it is only t square written there. So this coefficient should be equated to 1. Okay. Sorry, it is c square t square. It is c square t square. So we must write it as this bracket as c square as we have written here. So here we have 3 equations with 3 unknowns, and it should be now solved for a11, a44 and a44. Okay, and it is very easy to do. I am giving this you as an exercise, and you can show them that a44 you get it as square 1 divided by square root of 1 minus v square by c square, a11 as 1 divided by square root of 1 minus v square by c square, and a41 as v by c square square root of 1 minus v square by c square. All of this equation I call it equation number 6. And by substituting these values in equation 3, okay, we substitute a44, a11, a41, okay, so it was x dash equal to a11, x minus vt times a11, so it is x minus vt divided by root of 1 minus v square by c square, y dash is y, z dash is z, and we had t dash as given by this equation as a41x plus a44t. So if you substitute, we get t minus v by c square x, okay, root of 1 minus v square by c square, and this is equation number 7, and this represents the complete Lorentz transformation equations. Okay. Now for smaller velocities, v is much smaller than c, v square by c square is negligible in comparison with 1, and also vx by c square also becomes negligible. So here in the Lorentz transformation, we can ignore, this term will go to 0 as well as this term also will go to 0, and in the limit of low velocities compared to speed of light, we get that x dash is only x minus vt, y dash is y, z dash is z, and t dash is t, which is nothing but Galilean transformation. So in the limit of v much less than c, we say that Lorentz transformation equation reduces to Galilean transformation equation. These are the references for this module. Thank you.